Greetings. In this problem, we want to calculate how much bromine is formed when 2 moles of chlorine react with 4 moles of hydrogen bromide in a 10-liter container, noting that all species are gases. So we're going to first start off by writing out the reaction. And in this reaction, we have chlorine reacting with gaseous hydrogen bromide, and I'm going to leave out the phase just to keep the board clearer. And this is at equilibria with bromine and HCl, of which we make 2 of those. And we know that K is equal to 15. And what we want to do is calculate the amount of bromine produced if we have 2 moles of this and 4 moles of this in a 10-liter container. So what we're going to do is we're going to set up a Rice diagram, okay? And what we did is we started off with the reaction, and then we're going to write in the initial conditions, what we start with. Then we're going to have an expression to say how the reaction evolved as it went from its initial condition to equilibrium and the reaction was over. And then we need to have the equilibrium concentrations, which is how much of each species is present once the reaction is over. So what do we have? Realize that the equilibrium constant is an expression of constants. So if I have 2 moles in a 10-liter container, its concentration is 0.2 moles per liter. And we're going to put that in brackets to indicate concentration. And the concentration of HBr is 0.4 moles per liter. And we're going to have none of this and none of this. Now, as this reaction evolves, every time one of these react, 2 of these react. So we're going to go minus x, where x is the extent of reaction. It's a measure of how far the initial condition is from the equilibrium condition. And once the reaction is over, we have 0.2 minus x left over. Okay? So this is the equilibrium concentration, this is the initial, and this is the distant, how much it's evolved as it reaches equilibrium. Now in the case up here, and I can see that I did not properly balance that, there's a 2 HBr there. Every time one of these reacts, 2 of these react. So I have a minus 2x here. And every time one of these react, we make one of these, and we make 2 of these, okay? So at equilibrium, for the HBr, we started with 0.4, and we consumed 2x. For the bromine, we started with nothing, and we made x. And for the HCl, we started with nothing, and we made 2x, okay? So these represent the concentrations once the reaction is over and equilibrium is achieved. This actually represents Q, the initial conditions, the initial equilibrium expression. And this represents how the proportions of how they are consumed or produced related to each other. So we know that since this is a coefficient of 1 and this has a coefficient of twice, every time we consume one of these, we must consume 2 of those. Okay, now we need our equilibrium constant expression, K, and K would be equal to the bromine at equilibrium times the HCl, our products, at equilibrium squared. These values down here are the equilibria values. These values represent any time, divided by the reactants to the power of their coefficients. And of course, these are at equilibria. We often omit the E here. It's implicit when you say K, but I'm just putting it in here, okay? Now what we do is we substitute these values into here, and we get, okay, so what we have here is K is equal to x times 2x all squared divided by 0.2 minus x times 0.4 minus 2x all squared. Now, incidentally, a couple of comments before we proceed. In this problem, we have conserved the total number of molecules. Okay, we started with 3 chemical species, and we end with 3. And our reactants are in stoichiometric proportions. And if we had a mixture of these, if these were in stoichiometric proportions, we can use a technique called complete the power, or in this case, the power would be cubed, because we have an x times an x squared term and an x times an x squared term. Okay? So the strategy is to say k is equal to some expression where this is functions of x to the power of 1, okay, all cubed. So what we want to do is we want to factor the powers out and have everything there. Once we've done that, we can simply say that the cube root of k is equal to the cube root of this function, and the cube root is to the power of 1/3, and so that cancels, and I can easily solve for this. Okay? So I look in the numerator, and I can rewrite the numerator as a 4x cubed. Okay? Because recognize that that's 2 squared x squared, and x squared times x is x cubed. Now let's take a closer look at the denominator here. Because these are in stoichiometric coefficients and stoichiometric ratios, okay, this is 1, this is 2, and this is twice the size of this, I can factor out a 2 from here. So what I'm saying here is that 0.4 minus 2x is 2 times 0.2 minus x, okay? So when I do that, I'm going to do this in 2 steps. I have a 0.2 minus x times a 2 times 0.2 minus x all squared. Okay? Now, I can now rewrite that as a 4x cubed over a 0.2 minus x times a 0.2 minus x squared, which is a 0.2 minus x cubed. And then I had the 2 squared, which was a 4. The 4 over the 4 cancels. Now I have what I was looking for. I can say that this equals x over 0.2 minus x all cubed. So what I've now done is I've said that my k is equal to some function where there's only x to the power of 1, there's no x squareds or cubed or any other power, and that entire function is cubed. So now I can say that if I take the cube root of both sides, I have x over 0.2 minus x equals the cube root of k. Okay? Now does everybody see what I did? So what I did is I said, let me see if I have another colored marker here. I took this to the power of 1/3, and I took this to the power of 1/3, recognizing that 1/3 is the cube root. Okay? Now I can separate my, multiply both sides by 0.2 minus x because I want to collect all the x's on one side. So I have x is equal to 0.2 times the cube root of k. It's smart to put, when you multiply something by cube root, it's smart to put the number in front, because otherwise you may think it's part of the cube root, minus x times the cube root of k. So now I can say x plus x times the cube root of k is equal to 0.2 the cube root of k. Okay, now I can factor out my my x from this, and I have x times 1 plus the cube root of k is equal to 0.2 the cube root of k. So now I can say x is equal to 0.2 the cube root of k over 1 plus the cube root of k. Okay, now I can substitute my value of k, which was 15. So I have x is equal to 0.2 times the cube root of 15 over 1 plus the cube root of 15. Okay, and I get out my calculator, and I have 0.0142. Okay, now the question was how much bromine is present, and the amount of bromine at equilibria is x, so the concentration of the bromine, and I should put a 2 there because it's diatomic, is equal to 0.0142 molar. Now, if I'd been asked how much HCl, it would have been twice that. If I'd been asked how much HBr, it would have been 0.4 minus twice that. And if I'd been asked how much Cl2, it would have been 0.2 minus that, okay? Because X is equal to 0.0142, the extent of reaction, which happens to be the concentration of bromine because we started with none and the coefficient was 1. Okay, in summary, if you have an equation where the total number of species on the left-hand side equals the total number of species on the right-hand side, and you mix your things in stoichiometric proportions, you can use this complete the power technique as we've done here, okay? Hopefully that helps, and good luck.